Hello and welcome to this third video in our lecture on the TLS protocol. In the previous video, we discussed the authenticated version of the Diffie-Hellman key exchange algorithm. And in this video, I want to review it and study a couple potential weaknesses in it so that we can address them before we discuss how this algorithm is used within the TLS protocol. So remember that the Diffie-Hellman algorithm involves two parties. Let's call them Alice and Bob, or A and B. And remember that in the authenticated version, Alice and Bob are going to sign their messages in order to authenticate themselves to the other side. So this is going to be using a public key algorithm, for example, the RSA algorithm. And for this reason, each party is going to have a pair of RSA keys. Now, the Diffie-Hellman algorithm itself is going to use a pair of keys because it is also a public key crypto system. So we just have to remember that every time you're using a system and you want to use keys to support different goals, in this case, the authentication goals here with RSA, and here the confidentiality goal, we should be using different keys for these different functions. Remember that the goal of the Diffie-Hellman algorithm is to establish a shared symmetric key that will be used in the rest of the session to encrypt all of the messages between A and B. So remember, the Diffie-Hellman algorithm starts with two values, a large prime number Q, a primitive root of Q called alpha that everybody knows, including the two parties. And then there will be a piece of information, a number, x sub A, which is a random number selected by A that only A will know. And similarly, there will be private information to B called x sub B, which is a random number chosen by B. So we see that then the pair of keys for the Diffie-Hellman algorithm are the following. So first, I'm going to call this one the Diffie-Hellman public key for Alice to distinguish it from the RSA public key, and then the Diffie-Hellman private key of Alice. And you notice that basically the public key is going to be the Q and the alpha values. And then the private key for Alice is going to be this random number x sub A. And similarly for Bob, who also has to have a pair of Diffie-Hellman keys, we'll have a Diffie-Hellman public key and a Diffie-Hellman private key. And so his public key is going to be, again, the shared value Q and alpha, and then his private key is going to be the private value x sub E. Okay, so the next step in the algorithm after XA and XB have been chosen is for Alice to compute the following value, y sub A. And this is done by raising alpha to the power of x sub A and then taking the modulo of the result, modulo Q. And so this value YA is going to be computed by Alice and sent over to B, to Bob. And then Bob symmetrically is going to compute the value Y sub B by raising alpha to the power of his private key and taking everything modulo Q. So this will be sent from Bob to Alice. Now remember that in the authenticated version of this algorithm, to make sure that each party is authenticated to the other party, they're going to encrypt each one of their messages with their private key. So Alice is going to encrypt YA with her Diffie-Hellman private key, because here we're talking about authentication. And Bob is going to sign or encrypt with his private key the value of YB that he sends over to Alice. So eventually, then Alice will know her value Y sub A, and she will also know Y sub B after she receives it from Bob. And symmetrically, B is going to compute y sub B, and then is going to receive y sub A. So in a sense, both y values um, are shared by the two parties. And then finally, in order to obtain the final key, that is the goal of this algorithm, this is a shared key shared by A and B, so we're going to call it K sub AB. It's going to be computed using this y and x value. So in particular, Alice is going to compute the following value. She's going to take the value that she received from Bob. She's going to raise that to her own random number, and she's going to take that modulo Q. And on the other side, Bob is going to take the value he received from Alice, raise it to his own private key, and take the whole thing modulo Q. And the very cool thing about this algorithm is that those two values are going to be equal, and we proved that early on in the semester, and they're going to be what we call the shared symmetric key, K sub AB. So this is a brief summary of the authenticated version of the Diffie-Hellman key exchange algorithm. And so what I want to talk about in this video is a couple problems that you might identify here. So I want you to pause the video and think about the potential problems that you can see in this algorithm. Okay, so the potential problem number one is the fact that the two values y sub A and y sub B are not confidential. So make sure you see that because they are signed by the two parties, they are not encrypted. So notice that anybody can undo this operation by decrypting this message using the public key of Alice. And similarly, anybody can access YB by decrypting this message using the public key of Bob. And because these public keys are public by definition, anybody who wants them can get them. So YA and YB are not part of the private keys. In a way, they could be considered part of the public keys, although that's not strictly necessary. But the point is they are public information. So is that a problem? And remember, the goal of this algorithm is to establish a key that nobody else but Alice and Bob can know about. So how could an attacker use the information YA and YB to either obtain the key or be able to decrypt all the messages that are later sent encrypted with this key? Well, remember that the security of this algorithm depends on being able to solve the following problem called the discrete logarithm problem. So this problem is defined as follows: given that you know the following values, meaning alpha, q, and y sub A, then can you compute the value x sub A? Or if you're given or know the value y sub B, can you compute x sub B? It's the same problem, it's just symmetric. So notice that the way to approach this is basically knowing this value, and this value. Can you find the fourth value in this equation? And similarly in the second equation. So let's look at the first one. So the reason this is called the discrete logarithm problem is that this value that we are looking at is the number that you need to raise the number alpha to get y. So this is the logarithm base alpha of y. So this is why it's called the logarithm. And the reason it's called the discrete logarithm is because everything is done not in the real numbers, but in integers modulo q. So if you could solve this problem, then you can figure out the x A and the XB. And therefore, if you can determine the XA, you can use YB and Q, which are known, to compute the key. So is it a problem that these two values are known? Does they help you solve this problem? And the answer is no, because this problem is not solvable in practice. So given the state of knowledge in algorithms and computational complexity and so on, there is no efficient or practical solutions to this algorithm. And therefore, knowing YA and YB is not sufficient to break this cryptographic algorithm. So the bottom line is that this is not a problem. It's not an error in the design of this algorithm. This is actually a feature. It's not a problem because this discrete log problem is not solvable in practice. So we can forget about this problem, and it's completely okay to just sign the messages in the algorithm and not encrypt them. The signature is enough to authenticate the parties, and the encryption is not needed, assuming that the crypto is secure. And this is a good time to remind you that when we study the security of a protocol, there's two levels to consider. A protocol like this one uses some encryption algorithms like RSA and Diffie-Hellman. And so there's two ways to break this protocol. One is you could break the crypto algorithm themselves, or if these are secure, then we could abuse the protocol itself using, say, a person in the middle attack or some kind of modification to the protocol to use it in a way when it's not where it's not intended to be used to break it. Remember that from now on, we assume that the crypto is secure. So nobody can break the Diffie-Hellman, nobody can break the RSA algorithm. So now we're worried about weaknesses in the protocols. So the bottom line is that the fact that the protocol keeps those two values in plain text or available to everybody is not a weakness in the protocol, assuming that the crypto is secure. Okay, so that's the first problem that I wanted to mention. Now, I wanted to mention a second problem. I want you to think about it. So, a potential problem number 2 is the fact that XA and XB must be kept secret. Okay, remember these are the secret keys of the two parties, and they must absolutely be kept secrets. So the thing to realize is that each party stores one of these keys. So there's two places where the attacker could attack this algorithm or this protocol. And so what happens if one of the two parties is breached and their private key is revealed or exposed? What are the consequences? Well, the consequences are pretty severe in one sense, because once, say, X sub A is revealed, then all messages encrypted with the shared key K sub AB, they are become exposed. They can be decrypted by the attacker. So in other words, basically accessing the private key, of course, would be tantamount to undoing the encryption algorithm or breaking it. So the reason I'm mentioning this, and that might seem obvious to you, is that of course your private keys has to remain secret. But the question is there anything you can do to increase the security of that part of the system? And something that I mentioned earlier that I want to emphasize again and introduce a new concept is the fact that since all messages encrypted with this key would become exposed, then the consequence is that few messages or very few messages should be encrypted with this key. And of course, this key is nothing special. This is just a session key like any other keys. There are millions of such keys. So the bottom line is this is true for any session key, is that very few messages should be encrypted with each key. In other words, each key should be used with a small number of messages, which means each key should be used for a short amount of time. And this is the reason, again, that we discussed and introduced the use of session keys. Session keys are only used during one session. So this is our session key. In other words, this is the key that would be used after Diffie-Hellman has completed to encrypt all of the messages that are remaining in that session. But actually, there's something else that we need to do is, besides changing key for every session, we should also delete each session key as soon as it's not needed anymore. So not only the key should be used for a short session, a small number of messages, but it's very important that the key be destroyed after the session. Because remember that the attacker is potentially capturing and recording all of the messages between A and B. So even after the session has ended, the attacker could keep a record of all the previous messages in all the previous sessions. So it's possible that a week or a month later, the attacker could finally manage to breach one of the parties and retrieve or access their keys. But they won't be able to access those keys if they have been destroyed as soon as the session ends. So this is a new feature of the algorithm that I want to mention here, is that when an algorithm like the Diffie-Hellman algorithm destroys the shared key at the end of each session, we call it an ephemeral algorithm. So this algorithm that we're going to use in a TLS protocol is an ephemeral version of Diffie-Hellman. And you'll see that when it's described in the literature and even within the protocol itself, the string that they use for the regular Diffie-Hellman is DH, and then they add an E at the end for the ephemeral version of it. So again, the ephemeral version of Diffie-Hellman is exactly the one we saw in the previous slide, but the addition is that every session key has to be destroyed after or right at the end of the session where it was used. And so the reason for that is because there is a new goal now that we're interested in, and it's what's called perfect forward secrecy, or really perfect. I just struggle to remember what the F stands for. Yeah, sometimes I think of it as future, but it's really forward secrecy. So PFS. So what does that mean? That means it's not enough to keep the messages secure at the time that the session is ongoing, but it means it must also remain secure in the future. This is why I was worrying about the F here. And so, again, the idea is that if you were to keep a session key around stored on your computer or in your cache or somewhere, it doesn't matter if the session is over. If the attacker has recorded all of the messages in that session and they have access to that session key even a month later in the future, then they would be able to decrypt those past messages and still do a lot of damage. So to avoid that, the goal is to reach what's called perfect forward secrecy. And here the reasoning here is that you want to make sure that even in the future, so forward in time, nobody is able to go back and decrypt your messages if they get access later on to your secret keys. So this concept of perfect forward secrecy is implemented in the latest version of TLS, and this is why I wanted to bring it up here. And so to be clear about what perfect forward secrecy means, I can go back to this algorithm. And so what it means in particular is that as soon as this session is over, the values xb and xa have to be destroyed explicitly. And so that means that even if the attacker has recorded those messages, and even if a month later they breach one of those machines, they are not able to retrieve the value of x sub a, say, and therefore they're not able to compute the shared private key, because if they did, they would be able to decrypt all of the messages that followed this algorithm in the session. So this concludes our review of the authenticated ephemeral Diffie-Hellman key exchange algorithm.